Hello, welcome back. So, in the next part of the recorded lecture series, I'm going to start talking about subgroups. And in order to convince you that you really already know what I probably mean by a subgroup, I'm going to have you fill in this force space. Completely or force to your best of your ability, the answer to this question. Um, if V is a vector space, and I tell you that U is a subspace of that vector space, well, you can't read that now. Subspace of that vector space, what does that mean? All right. So maybe you tried to remember the technical conditions that are like U is a subspace if and only if it satisfies these conditions. But there's a very simple answer. It's one that isn't used when you want to prove something is a subspace because there's more stuff to check. But the short answer is V is a vector space. U is a subspace of V if two things happen. One, U is a subset of V, and U2 is a vector space. And maybe I'll put some parentheses because maybe there's something worth adding here. Right, you're not allowed to use a different sense of addition and scalar multiplication. It has to be the same one. Inspired by this, if G is a group, then I will say that H is a subgroup of G if two things happen. One, H is a subset of G. And two, H is a group. And this isn't always what a mathematician will mean when they say something about this object is a sub-blah of that other object. But quite often it's what that mathematician will mean. A subgraph is a subset of a graph that's still a graph. A subspace is a subset of a space that's still a space, whatever the word space means. A subgroup is a subset of a group, which is still a group. So let's just check some examples. Here's one I claim. The set containing the equivalence class of 0, the equivalence class of 2, and the equivalence class of 4 is a subgroup of Z mod 6 under addition. So let's remember what you need to do to prove something's a group. You need to show it's closed under the group operation, and I have to use the same group operation as G. That's part of what it means to be a group. Right? If you like, it's the thing that I wrote in parentheses over here. H is a group under the binary operation that makes G a group. So the first thing you need is closure. Let's fill in a Cayley table. We've used this before to check for closure. We do that real quick. 0 plus 0 is 0. 0 plus 2 is 2. 0 plus 4 is 4. And this thing's commutative, so I already know what that column is going to be. 2 plus 2 is 4. 2 plus 4 is 6, but 6 is 0. 4 plus 2 is 6, but 6 is 0. 4 plus 4 is 8, but mod 6, that is 2. And let's just do a quick check. Closed just means that when you add together two elements of this subset, you get something in that subset. Yeah, looks like. When we add two elements of 0 to 4, we get an element of 0 to 4. So it is closed. Neato. Associativity. Again, this is going to be automatic. addition is associative on all of Z6 because it's a group. So it is associative on 0, 2, 4. Nice. Identity element. What do you think the identity element of this thing is? Yeah, that's what it has to be. 0, right? 0 bar is the identity in Z6. So 0 bar, yeah. Zero plus x is equal to x, no matter what x you pick in Z mod 6. And in particular, for any x in 0, 2, 4, because it's a subset of Z mod 6. Inverses. Well, let's just check one at a time. It's an additive group, so we put a minus sign instead of an inverse sign. Minus the equivalence class of 0 is the equivalence class of 0. Good. Minus 2. Let's see. You need to now reduce that mod 2. Negative 2 is the same as 4 mod 6. So each element of 0 bar, 2 bar, 4 bar has its inverse in 0 bar, 2 bar, 4 bar. All right. There are two obvious examples that are just subgroups no matter what group you start with. If I give you any group G, and 1 is the unity element of G, then here's one example of a group. The set containing only the unity element. Another one, all of G, is also a subgroup. And you know what? Like, if we were in class in Boston, it would be like some really good shtick to let you decide which one we're going to do, but can't do that. So I guess we will check it for first one on the list is 1. So what are the things you need to check for something to be a subgroup, to be a group? I definitely know that singleton 1 is a subset of G. So let's start by saying that. Singleton 1 is a subset of G. Good. We need singleton 1 to be a group. If we can do that, then we are done. All right. Well, what do you need to be a group? It needs to be closed under multiplication. Closure. Let's take any element of this set, 1. Let's multiply it by any element of this set, 1. Well, 1 times 1, no, I don't need a line on top of that. I don't mean, this isn't like a congruence class. Identity times the identity is the identity. So, singleton 1 is closed. Associative. This is, again, like the obvious one. The binary operation, which I guess I'm calling dot, is associative on all of G. So it is associative on any subset. So I'm kind of leading into this logic that you don't need to worry about whether or not the binary operation is associative on a subset. That's not something you need to check to get a subgroup. All right. Um, associativity, that's good. There's an identity element. Well, one is the identity element. And right, what would you need to do to check that? You need to check that one times anything in that set is one. Only thing in that set to check is one. One times one is one. Cool. Inverses. One inverse is equal to one. So singleton one is closed under inverses. Well, that's all the conditions. Singleton one is a group. So you'll notice some things in the logic of the previous two, just checking that things are subgroups. There's some stuff that we kind of could have skipped, like, or at least that didn't use anything about the particular thing we were talking about. Associativity. This argument didn't care what subset I was studying. So I think we can just like not bother checking for associativity on a sub on when we're checking that something's a subgroup. Um, as a consequence, we'll get the following theorem. Theorem 3.3.3, the subgroup test. This is version one. It's the one that's slightly longer looking. If G is a group and H is a subset of G, then H is a subgroup of G if and only if three things happen. H contains the identity. Let's see, maybe I'll call the identity E this time. E is in G, where E is the, well, all right, I've been kind of inconsistent with notation. Should I call it the unity or the identity? The two words are being used interchangeably, and you should get used to both of them. I guess in this context, I'm calling it the identity and not the unity. Oh, and I've also said it wrong. I know that E is in G already. I need it to be in H. So H has to contain the identity, meaning that E is in H, where E is the identity element of G. It's closed under multiplication. Well, you know what that's got to mean. I don't know. P times Q is in H for all P and Q in H. And there's nothing special about the letter P and Q. Oh, the recording was a little behind. Sorry if there was some vagary that happened because of that. Um, closure under inverses. So, what does that mean? It means that for all, let's call this one little h in big H. Well, I know that H has an inverse in G because G is a group. So I can talk about H inverse. It is in H. And maybe I'll just add something for clarification where H inverse is the inverse of H in the original group G. So what does that say? That says if you want to check that a subset is a subgroup, you don't need to check all of the conditions of a group on that subset. You just need to check those four. Associativity comes for free. So let's go through and write down a proof. So let's explain why this H satisfies all of the conditions of a subgroup. So I guess one, H is a subset of G by assumption. And I'm being informal, so I'm not going to like declare all the assumptions of things. But there's one of the assumptions in the theorem. H has to be a subset of G. Next, I need to check that H is a group. So in order to check that a thing's a group, what do you need? you need H is closed under the binary operation. Oh, but that's just like one of the assumptions. That's assumption 2. What else do you need? Associativity. Well, maybe I'll say this in all the WADs. For any P, Q, R in H, we have P, Q, R in G, because H is a subset of G, as dot is associative on G, since G is a group, P times Q times R with parentheses, arrange the Foster is the same as P times Q times R. Oh, wait, we've just shown that for every P, Q, and R in H, we can move parentheses when we multiply P, Q, and R together. So multiplication is associative on H. And that's kind of what I meant. You don't need to check associativity. You just inherit it from G. All right, cool. What's next? There has to be an identity element. Oh, that's assumption 1. By assumption 1, H has an identity element. And last thing is inverses. If I take something in H, it has to have an inverse. Oh, that's just true by 3. By 3, every element of H has an inverse. In H. All right. Cool. So let's just say what this means. Thus, if H is a subset of G and conditions 1, 2, and 3 hold, what do I mean by conditions 1, 2, and 3? I mean the conditions in the statement of the theorem. Then H is a subgroup of G. And maybe I didn't say this as loudly as I should have. There's a notation we'll use for subgroups. I'll use this less than or equal to sign for a subgroup. If you like in LaTeX, that's /LE. That's established right here. When H is a subgroup of G, I will write H less than or equal to G. Cool. All right. There's also a short version of the subgroup test. Let's just say what that is. If G is a group and H is a subset of G, then if I were to show H is a subgroup of G, I can just check 2 conditions. H better not be the empty set. And if I take 2 things in H, then H2 multiplied by the inverse of H1 needs to be in H. Those 2 conditions will get me everything I need for any subset to be a subgroup. And right there, upstarts and downstarts of using 3.3.4 as opposed to 3.3.3. They'll both get you the same result, so you can use either. 3.3.3 has 3 things you need to check. 3.3.4 only has 2. And in fact, item 1, you just need there to be something in the set H. You don't care if you find the identity in the set. You just need to find something. 3.3.3, you have to show the identities in H. On the other hand, the identity is probably the easiest thing to show is in a set. All right, well, that's enough of that. Let's actually sketch the proof of this. So let's let H be a subset of G, satisfy these conditions. Well, since H is not empty, there's something in that set. H is in H. Let's explain why 1 is in H. And this is where condition 2 is going to start doing lots of heavy lifting. let's see, as H is in H and H is in H, assumption 2 says H times H inverse is in H, right? If I take any H1 in the set big H, so I can take that to be H, and I take any H2 in H, well, I can take that to be H, then I know the product of H1 times H2 inverse has to be an H. Oh, cool. That means I could have taken both of them to be the same H. Thus, E is in H. Though I guess right now I seem to be calling the identity element unity element 1, not E. But you can use either notation you want. You can use the notation of E for the identity or 1 for the identity. You just have to be consistent. All right. Well, I need to show that H is closed under inverses. But now I know two things are in the set big H. I know little h is in H, and I know 1 is in H. And in fact, maybe I don't care about little h right now. Let's let P be any element of H. I need P inverse to be in H. Well, that condition 2, this is something that I have no matter what H1 and H2 I pick. Well, since E and P are in H, by assumption 2, I conclude that E times P inverse is in H. Thus, P inverse is in H. That verifies that this set is closed under inverses, which is one of the things in this. So far, I've got it to contain the identity. I've got it to be closed under inverses. Now I need closure under multiplication. So let's do that. Let's let P and Q be in H. I need PQ inverse. Nope, that's the thing I get to assume. I need to show that PQ is in H. And let's go off to the side and see if we can figure out how to do that. Let's see, I need P times Q to be in H. Well, the assumption I have is that PQ inverse is in H. In fact, the assumption I have is better than that. That Q inverse, that Q could be any element of the set big H. Oh, well, Q inverse itself is in big H. PQ inverse inverse. I wonder if Zoom is showing you this message that I'm seeing that's something my internet's unstable. Hopefully it's not a big deal. So I know this is in H by the thing we just proved. I think that does it though. PQ inverse inverse, that's PQ. So let's do that. By closure under inverses, and maybe I'll add a cheeky little line here, which we just verified. All right, sometimes you want to like even accommodate a reader who has very bad short-term memory. We just checked that H is closed under inverses, so we can use it. You can use that fact. We know it's true. By closure under inverses, Q inverse is in H. Oh, cool. Thus, by assumption 2, P Q inverse parentheses inverse is in H. Ooh, Thus, PQ is in H, and H is closed under multiplication. So maybe instead of like emphasizing the shortcomings, let's see what we have done. Thus, if conditions 1 and 2 hold, then H satisfies the conditions of theorem 3.3.3. But theorem 3.3.3 concludes that H is a group. So H is a group. Nice. Very good. So now let's address this bullet point. Like, let's think about what we've done. We've shown that if 1 and 2 are true, then H is a subgroup. This is an if and only if group. In order for this to really be complete, I need to prove the other way. No, I'm not going to write the word technically. And, well, I'm not going to write anything. I'll say some things. Well, why, if H is a subgroup, that means it's a group. Groups contain a unity element. If something contains the unity element, then it contains at least one element. Non-empty. Condition 1 follows. So I get that one. Uh, if I take two things in H, well, I know H is a subgroup, so I know it's closed under inverses. Oh, so H2 inverse must be in H. Groups are closed under multiplication. So H1 times H2 inverse must be in H. Yeah, okay, so that one's actually like, the reverse direction is free. All right. So here's one that I'll have you do real quick. The alternating group is a subgroup. And in fact, I think I'm going to write nothing. You should read theorem 2.3.20 and then decide which of theorems 3.3.3 and 3.3.4 seem most appropriate. Cool. Well, now that you've done that, let's just go back to 3.2.20. The PDF viewer that I use, unfortunately, isn't hyperlinked, so I can't click back. 2.3.20. So I'll have to do some scrolling. By quite a bit of scrolling. Previous chapter, right? 2.3.20. Can I do things this way? Nice. What can I do with that? Okay, no, not going to worry about that. So let's look at these conditions. The identity is in AN. Ooh, so that means AN has the identity. That's a condition in one of the two theorems we have. If I take two elements of AN, then so is sigma delta inverse. This makes me think that I want to use the short version. So now I'll have to try to keep my really bad short-term memory active because I'm going to have to cite that theorem. By theorem 2.3.20, epsilon is in AN. And maybe for the sake of what we're calling epsilon is the identity permutation. And since I think I want to use 3.3.4, I'll say thus AN is not empty. Ooh, also by 2.3.20 for all, I think they were called sigma and delta in the theorem statement. In AN, sigma composed with delta inverse is in AN. Thus, all of the assumptions of theorem 3.3.4 are satisfied, and AN is a group. In fact, no, let's use like the technical symbol. AN is a subgroup of the group SN. All right, cool. I think again, I'm going to pause the recording here. I will meet you in a moment with the next part of this series.